four key parts to it. What's called the summand, the thing inside the sigma symbol. The index, which is your variable. That's your independent variable like in functions. Lower limit and upper limit. Right? So let's look at the sum from k equals 1 to 100 of k squared. How do we express this? How do we expand this out?
1 squared 2 plus 2
1 squared plus, that's implied by the sigma, 2 squared plus 3 squared plus dot, 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 100 squared. So 1 and 4 and 9 and 10,000, that could be quite a bit of work, right? Maybe we have a shortcut formula. How about we use S sub n equals T sub 1 times 1 plus, no, I'm sorry. S sub n equals n times T1 plus Tn over 2. How's that sound? Or do you want to use this one? S sub n equals T sub 1 times 1 minus r to the n over 1 minus r. How's that sound?
No, it's the first one.
It's the last one?
Yeah.
Should we put it to a vote? How many said the last one? Raise your hands.
Wait.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many say the right one?
We don't know.
None. How many say neither?
Oh, we don't. Oh, I say neither.
Why, Joe?
Because I don't think we know R, do we? Or N?
This is for an arithmetic series, right?
Yeah.
Is this arithmetic? No. This is for a geometric series. Is this geometric? No. So you can't use either of these people. What are you thinking? I'm putting happy faces down, but I'm most displeased. Okay? No, we can't use any of those tricks, can we? So you have to do it by hand. Let's see what the calculator says, all right? Let's try it on the TI-89. TI-89. Get your sigma out. I have one available here. If you promise not to take it for 24 hours, you may borrow it. Maybe you should bring back the topic of taking the driver's license. The driver's license? Then I'll have that. No, please, keep your shoes on.
Take his glasses.
Sum of what goes here in this first argument. K squared. This would be, what's our new term for that? The summand. Then what? K, and our new term for that? It's the index. It's pointing to where you are in the sequence. And then we have the limits of summation from 1 to 100. And these are the limits of summation. As we said. Okay? And you should get a huge number, some 300. Okay, how am I supposed to understand that when you start different points, like you cacophony of sine waves that are all on stage? Zach?
338,000.
Yes?
350.
350. That's huge.
0, 0.
You may want to shift out of fixed 2 to floating 12. Okay? Float 12, that would help. Okay, another summation. So negative a half to the first, plus negative a half to the second, plus negative a half to the third, plus negative a half to the fourth, plus negative a half to the fifth. So negative a half and a quarter, and negative an eighth, and a 16th, and negative a 37th. Okay? Now, hold it. Don't we have a formula we could use?
Yes.
Which one? T sub 1 minus r to the n of 1 minus r. But by the time we plug that formula in, we could have just evaluated this because it's not that bad, right? It's negative 16 and 8 and negative 4 and 2 and negative 1, 30 seconds. Or negative 11, 30 seconds. And you can check that in your calculator too. Okay. Now actually, I said you'd have to do that on your calculator or painstakingly add them all. Oh no. We're going to have a formula for this that you will memorize as soon as possible to add the sum of squares and cubes and whole numbers. Summation of j equals 0 to 8. Now before you just say 1, careful what the indices are here. We start with j equals 0. So a half to the 0 plus a half to the first plus a half to the second, not to infinity there. So 1 and a half and a fourth. Is it geometric?
No.
Yes. The common ratio is a half. The first term this time though is 1. So when you use our infinite geometric sum formula, t sub 1 over 1 minus r, 1 all over 1 minus a half, we can get 2. And we showed the other day how you do this in your calculator. You can put infinity in the sigma notation for your upper limit. I don't think it's going to like it if you put infinity down for the lower limit. But you can try it. Yeah, what happens if you go from infinity to infinity? Probably doesn't like it. Okay. Now, some properties of finite sums. Because this is a very key topic for what you're going to do in calculus next year in terms of the interval. And you might think, do we really have to memorize all these huge formulas over here later on? Oh yes. And here's why. Because you can think of the area under the curve. This is a quick sketch. You don't have to put this in your notes. Area under the curve by making a bunch of approximations with rectangles. Does that look close to that area under the curve? We're missing bits, right? So what we do then is let's do a better estimate by making more rectangles. And so if we let the process go to infinity, we'll get the exact answer. So it's like that infinite sum we saw before, where if we let the number of rectangles keep increasing, it's going to get more and more complicated. We'll have to add up big sums like the one we talked about before. But if we look at the process as it goes to infinity, it'll give us the area of the curve. Much like the other process we talked about, turning a secant line into a tangent line, you also have to look at a limited process. All right, now first I want to make sure you understand these are subscript i's. Can you see that in the back of the room there? But these are not ones, this is a sub I. So it becomes, put 1 in and you get a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus dot 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 all the way up to a sub n plus b sub n. So how could we rearrange that? As two sums. Added up. But sums of what? A sub I, B sub I. Because this will be A1 plus A2 plus A3 all the way up to AN. And this one will be B1 plus B2 plus B3 all the way up to AN. And sigma stands for sum up, so it's a bunch of additions. And it's just the associative and commutative properties of addition that let us rearrange this and pluck all the a sub 1s out. But now you have to be very careful though when we have multiplication. If I multiply a constant times each of my terms, now I've got c times a1 plus c times a2 plus c times a3 plus dot 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 all the way up to c times a sub n.
So is it just c times the sigma?
You can factor out the c. And so, yes, c times summation of what though?
AI.
Of a sub I. So a constant multiplier we can sort of move outside of the sigma notation because that's the distributive property in reverse. But I want to add one in here. What about the summation from I equals 1 to n of a sub I times b sub I? What do you want to call that? Because remember, this is going to be a1 b1 plus a2 b2 plus a3 b3 all the way up to a sub n b sub n.
You can combine what we just did. You can put ai plus b. Okay, sigma
ai
plus
sigma bi. Right? You like it?
Yes. But no. You need to add them there.
Why don't you like it?
Because you need a factor.
This is A1 plus A2 plus all the way up to AN. This is B1 plus B2 plus all the way up to B sub N. When you multiply these, you'll get these terms, and then some, right? How many more?
Over 9,000.
Not ginormous. It's n terms by n terms. How many terms do you get in the product then?
N squared.
N squared. How many do I have down here?
Oh, so does that
N. So we're just going to get n squared minus n more terms.
So does that have to be the square root? Or take the nth root of that?
When you want to take the square root of something here, you've got a big mess here. So it doesn't multiply out like the dot product or something like that, right? This isn't a dot product. So, no. Let's get the big no in the rainbow. No. The summation idea doesn't distribute over multiplication. So it's not like limit. Limit, we were pretty liberal with that, right? Distributing over multiplications, additions, subtractions. Looks like it just distributes over addition. And the only reason we're pulling this C out with this multiplication is because it's a constant multiplier. The same ideas will come up again in the integral next year, so start getting used to them now with summations. Okay, now commit these formulas to your memory. Now, start the process now, finish it tonight by 11:59, okay? And you will be ready. Sum of integers. Do you remember this one? If you take 1 and 2 and 3 and 4 and 5 and add them up and get up to n, there's a little formula for it. They're called the triangular numbers because this is 1. S sub 1 equals 1. S sub 2 equals, oh, look at the little triangle. That's 3. 1 and 2 is 3. S sub 3, that's 6. S sub 4, I think you've played this. Don't lie to me, if you're in Milwaukee, you've played this. 10.
The dot game?
And no, this one. Trouble with capital T rhymes with P, it stands for
Pool.
pool. Yeah, S sub 5 is 15. 15. Where'd you get that?
In the book.
Oh, gosh. All right, Bill just knows it. N plus 1 over, n times n plus 1 over 2. Let's do our proof, though. This is clearly arithmetic, right? It's arithmetic. And so we can use our arithmetic sum formula, which is n times t sub 1 plus t sub n all over 2. How did you get your formula, Bill?
Prove it. Well, I just...
What's the first term? 1. What's the nth term? N. Okay, now, watch out for that. That's right in this case because we have the identity series. That is t sub n equals n. Normally t sub n is a whole other formula, right? But the identity series works out to be this. N times n plus 1 over 2.
So it's a t sub 1 plus t sub n.
Yes, that's the formula for arithmetic. Now, here we go. Here's some more. Okay? Let's actually jump down to sum of cubes. And we'll prove these with our inductive ideas on that first Monday back. Now, before you go, oh, it's a good thing it's a week after that Monday. Just so you know, that week back is only a 40 week. Woo! Monday through Tuesday. We're going to test these on that Monday. Yes, it's the day after Easter. Plan your family events accordingly, okay? Some of you don't celebrate Easter, other than that, okay?
Oh wait, that's Easter.
Yeah, well, that's why you got Good Friday. You're all done, okay? Let me give you a little mnemonic device. Bill has already mastered the sum of the integers, n times n plus 1 over 2. All you have to do is square his answer, and you've got the sum of the cubes. N squared times n plus 1 squared.
Yep, Bill.
Okay. Yeah, it's really good. You must know.
I get excited.
But that's his name.
Now the sum of the squares. A little trickier.
Is it going to be a geometric sequence?
No. It starts off like the other ones, n times n plus 1. But let's throw in a little 2n plus 1 for good measure, okay?
What?
All over 6.
What?
We'll prove this next week, okay? Or actually in 2 weeks. That's the sum of squares. N times n plus 1 times 2n plus 1 over 6. And you know there's one for the sum of 4th powers too, but I haven't committed to that yet. Okay, Julia?
So could we have used that?
Yeah, and let's check it. Let's check this on that other one we did here. But before we do that, let's just practice using them on some small ones like this. Let's practice using some of these. Okay? Now, first we're going to do it the brute force technique. Brute force is you just expand it out. 1 squared plus 2 squared plus 3 squared plus 4 squared. It's not that bad in this case because you got just 4 terms you're looking at. 1 and 4 and 9 and 16 makes it crisp
32.
30. Okay. Let's contrast it though with the finesse technique. I think that's where I put the accent. Okay. And that is not to grind it all up, but to use the formula. The finesse formula technique. We have a formula for the sum of the first n squares. It's n times n plus 1 times 2n plus 1 all over 6. What's n in this case? 4. So that'll be 4 times 5 times 9er over 6. 180 over 6 is 30. Check, please. There you go. Okay? Now, you might say brute force was easier. Yeah, for this problem. But let's go back and check it on the other one. Thank you. Just while I'm talking, somebody else is talking. Yeah, you know who you were.
I was talking to myself.
Not good. Okay? You and Dick Van Dyke can do that. Not him. Okay? Now, let's try that formula over here. On the one we did here, they would say, oh, it's impossible. You can't possibly do this without a huge calculator. Or a UNIVAC system or something. No, you can do it. How? By the formula. It's close to the force. N equals 100. So we get 100 times 101 times 201 all over 6. The 3 will go into the 201 nicely, right?
Yes.
2 will go into the 100. That's 50 times 100 times 3 into 201. You need 67. So that's all you got to do. It's 67 times 50, 50. 67 times 50, 50. Oh, yeah, 6. 3, 5, 3, 5. Check out the 3s here. Oh, 0, 30, carry, 3, 3, 3, 3, 8, 3, 5, 0. Yes! See, it can be done by hand. Okay? And this is what I expect you to do on the test. You should be able to do this one now by hand. Express this first in sigma notation and then evaluate. Without a calculator. But I'll show you where I let you start bringing up the calculator for the arithmetic. Okay?
Do we have a calculator on the test? Or just on that?
That's why I passed out syllables.
Yes.
Because it says you're allowed it for some of the arithmetic. But in this case, I wouldn't want you to just sort of, well, first of all, how would you enter your calculator anyway? You need to come up with a formula for the nth term anyway. Right?
We need to get answer 1.
So let's get that in a second. I don't think it's going to work well that way, okay? Are you trying to do recursive definition of this?
I think he is, yes, sir.
Let's look at the parts. See, if you write it as 2 plus 12 plus 30 plus 39, 3980, no, not that one. Look at the parts. The first factor is 135 all the way up to 199. You recognize what kind of sequence this is? Arithmetic, common difference of 2, first term of 1. So we can write a formula for the nth term. It's 1 plus n minus 1 times a common difference 2, or t sub n equals 2n minus 1. Similarly, we've got 2, 4, 6, all the way up to 200. That's arithmetic 2 with a common difference of 2, but a first term of 2. So t sub n equals 2 plus n minus 1 times 2. So you get t sub n equals 2n. These are key because this is basically how you express odd numbers, and these are even numbers. And if you want to memorize those two, it might save you in setting up some explicit formulas in the future. Now, we want to get into sigma notation now. And did we figure out the number of terms? 100. Yeah, 100 terms. The number of terms, we can set 199 equal to 2n minus 1. So we get n equals 100. That's going to be handy. So now we're ready for sigma notation. Summation from... Oh, you want to use k? It's fine. K equals 1 to 100 of 2n minus 1 times 2n. No. This is wrong. Intentional mistake to see if you're awake.
Oh! We need to use the formula we just learned, right?
No, just multiply.
No, but you can't
No.
multiply.
We can't multiply.
We can't
You
multiply.
cannot multiply.
This is wrong.
Yes.
I'm going to get my micro eraser.
No.
It's a little mistake, but it's a key mistake. Why do we have an index?
To show the upper and bottom limits.
Right, but
Oh,
also
you have to use K. Oh,
to
K and
specify
N.
what your variable is.
K and N.
So you have to use K in here, or it's not going to change.
N is not.
Thank you, micro eraser. There we go. K, 2k minus 1, 2k. I know we said n over there, but, and we could have gotten by if we said n equals. But I kind of like n to represent the number of terms you're going to add up. So use some other variable then, to get less confusing, use some other variable like I, j, or k then for your index variable. Okay, so that's just part 1. And you can put it in the calculator and get an answer. Do we want to do that right now? Just forget it. What does the TI-89 say? But you must do this by hand.
I got 1 million.
It's part of understanding the integral next year. You're going to do a lot of limits. What does the calculator say there?
1,343,300.
Wow, that's huge.
It's a big point.
How do we do this by hand? How do we use the summation formulas and properties that we just talked about to do the summation from k equals 1 to 100 of 2k minus 1 times 2k? What do we do with the sum of a product?
You can distribute it out.
Distribute it first.
So you get 4K.
There is no distributing the summation over multiplication, so you're going to have to expand this out, get terms, and then you can distribute the idea over the terms. So you got the summation from k equals 1 to 100 of 4k squared minus 2k. So it's a summation from k equals 1 to 100 of 4k squared minus the summation from k equals 1 to 100 over 2k, of 2k. So we distributed over subtraction. Now what? These don't match my formulas yet. Nothing talks about the sum of 4k squareds or 2k's.
You can put the 4 on the outside.
That's the constant multiplier. 4 times the summation from k equals 1 to 100 of k squared minus 2 times the summation from k equals 1 to 100 of k. Now, because you don't have these memorized yet, I'm going to go back and make a copy. We need the k squared formula, right? Remember that one? Yeah, it's right there. all its beauty. Boom. Yeah, that's it. There's our k-squared formula. Let's cut it and go. Make it a little smaller so it fits in here. Can you see it okay? There's the formula. That's the one you're going to apply right there, right? And we also need the other formula while we're at it. Do you remember that one? There you go. It's right there. Okay. Cut it and go. Okay, let's practice using them. So it's 4 times this summation. N is 100. So it's going to be 100 times 101 times 201 all over 6. Minus 2 times this summation formula. It's going to be 100 times 101 divided by 2. Well, that last part isn't too bad, because that's 100 times 101, 10,100. This one's going to be a little bigger though, right? And we already did this, and didn't we get that 343,000?
It was 338,050.
350?
Yeah.
Okay, times 4 minus 10, 10,100. And you get 1,382,000. 343,000?
Yeah.
Oh, because of the subtraction? Comma. 300. Okay. That's how I expect you to do it by hand. Now, at this point, I'd let you put all this arithmetic in the calculator. Okay? Right? Because that could take a while just to grind out. But the key is that you understand how to take this summation process and apply those formulas. Because that's essentially how you're going to integrate x squared and x cubed. Okay. That's it. You got a big weekend coming up here. Let's take a look at how the tote board's doing here. Not bad, not bad. We got some more you can fill in here. Some people have some assignments they can give me. That's what I want to see. Okay, let me just shut this down here. Stop.